And I'd like to welcome Elias Arnold from the University of Heidelberg.
Exactly, yeah.
Perfect.
So yeah, hi everyone. My name is Elias Arnold. I'm a PhD student at Heidelberg University, and I work on applications for analog event-based neuromorphic hardware. And I'm particularly interested in scaling up training for functional modeling and high-level modeling APIs on such hardware in order to improve or approach more interesting tasks in the future. And today I want to give you a brief overview about our recent efforts in scaling up training on the BrainScales 2 system. Sorry, I forgot this one. So first, let me give a short overview. I want to bring everybody on the same page in what we mean about analog event-based neuromorphic hardware. Then I want to give an overview about the BrainScales 2 experiment platform. Then I want to talk about multi-single chip experiments and data sparse learning. And in the end, I will give a short outlook. So, as most of you probably know better than me, the brain is known for its relatively low information processing capabilities while performing multiple very complex tasks at the same time. And this is believed to be due to its sparse event-based communication of fire or so-called spike events between neurons, which perform computations in continuous time. And analog event-based neuromorphic hardware implements those working principles in physical computing devices to mimic brain behavior. In particular, we have analog synapse and neuron circuits implemented on those devices in order to hopefully realize fast and energy efficient beyond von Neumann computing. Yeah. So one such analog event-based neuromorphic hardware system is the BrainScales 2 system, which is developed in our group in Heidelberg, and it features 512 analog adaptive exponential neuron circuits, where each neuron circuit is individually configurable with a fan-in of 256 inputs. And we also can combine or shorten multiple neuron circuits on chip in order to form larger, more complex neuron types, and also to increase the fan-in to a logical neuron on chip. Yeah. So it's important to note here that the neural dynamics, and it's not simulated, but it's actually implemented in analog circuits. And as you can see here, as an example of an analog membrane trace on chip of a single neuron. So the neuron dynamics on chip has a speed-up factor of about 10 to the power of 3 compared to biological time constants, which makes the BrainScales 2 system an SNN accelerator. So facilitating experiment execution on special purpose hardware is crucial for non-expert users to use or run experiment on such hardware seamlessly. And for BrainScales, users can create their own experiments in their own environment using the BrainScales 2 software stack, which is also part of the eBrain software distribution, which is deployed on all the eBrain's HPC sites, as well the eBrain's Jupyter Lab. And using the software, the experiment is translated into a hardware experiment description, which is uploaded to our experiment service, which runs at our cluster in Heidelberg, which then schedules and eventually executes the experiment on the BrainScales 2 hardware, and then returns the corresponding hardware or the desired hardware observables, like membrane traces or spikes. Yeah. Currently, we have BrainScales 2 multi-chip setups in the commissioning phase, but so far only single chips setups are supported. But yeah, we will support multi-chip setups in the future. And we also are working on providing means for digital optimization directly on the ICNCE cluster in Heidelberg. So one approach to machine learning on BrainScales 2 is in-the-loop training, which has been demonstrated for multiple different experiments. And here we use the support of established machine learning frameworks in which the user can describe or define spiking neural network models and use the framework to optimize the parameters of the model. As for machine learning frameworks, we are currently supporting the JAX as an HX torch, which is based on PyTorch, as well as JAX as an N, which is, or we call it Jackson, which is based on JAX, which allows for event-based gradient estimations. Using this software, the user basically just defines their models in like high-level software, and then the software finds a hardware experiment description using the parameters in the topology, maps the experiment to hardware, and then executes it using the inputs. And after execution, it returns the hardware observables like spikes or membrane potentials in the framework-specific data types, which are then used to optimize the parameters on the of the model using the optimization method of the corresponding framework. Yeah. Currently, in high-level software, this has only been demonstrated for a single chip experiments where the spiking neural networks had a size that fit on a single chip instance. But obviously, this is a great restriction because most real-world tasks or interesting tasks typically require larger networks than the size of the chip, and for this we want to create or build multi-chip systems where you can partition the larger network into a couple of subnetworks where each subnetwork individually fits on a single chip instance, and then those subnetworks can be executed concurrently on the while communicating spike events in real time via FPGAs. Yeah, so this allows to run larger scale networks by means of partitioning. So currently those systems are in the commissioning phase, but building new hardware is typically very expensive. So you really want to have means for faithfully testing future scale system without having to build them right away. Because this effectively allows hardware model co-development, which ensures that the future scaled hardware system is suitable for the algorithms and models that you intend to run on those systems, as well as to guide algorithm development to sort of respect the constraints of the hardware development. Currently, as we don't have yet multi-chip setups, we partition larger scale networks into smaller networks, and then instead of running them concurrently, we run them sequentially, as you can see here, where we hold and merge data that is required for a partition that is later in the computational graph in software, and then basically just execute them sequentially. And this is all supported now in our high-level HX torch framework, which makes it very easy for users to write down and execute larger scale networks in the software. Or on brain scales, yeah. So we have demonstrated this within the scope of a project with the European Space Agency in which we investigated spiral neural networks for land cover or scene classification of satellite images, which you can see here. Those images have the size of 64 by 64 by 3 inputs, and those inputs were translated into a spike representation using time-to-first spike encoding. And for classifying those images, we considered a 3-layer network with 2 hidden LIF layers of size 484 and 128, projecting onto 10 leaky decision readout neurons. The input projection can be mapped to one chip instance using the chip's internal support for sparse connectivity, which you can see here. And in this case, we had 3x3 receptive fields, like 3x3 receptive fields projecting to one neuron in the first hidden LIF layer. In the second layer, we had 128 leak integrated fire neurons, where we represented the necessary fan-in of 484 from the previous layer by connecting 4 hardware neurons to form one logical neuron on chip. So for this, we observed a hardware penalty of about 9%, but this project was really about achieving accuracy from the simulations, but rather to show that we can emulate those models on the chip. And we believe that further tuning will bring the accuracy closer to the expected accuracy in simulations. So for in the loop learning on brain scales, currently the bottleneck is the data transfer from the recorded data that is stored at the FPGA to the host computer, which is needed to compute weight updates, as well as the limited trace memory where all the data is stored, so you cannot run or record your experiment forever. And therefore, modeling on brain scales 2 greatly benefits from data sparse training algorithms. For instance, for the Euroset dataset example, we use surrogate gradient-based learning, where you typically rely on spike recordings as well as densely sampled membrane recordings in order to compute the gradient or the surrogate gradient, which also requires the recorded data to be translated into a data format with fixed, where the data is represented on a fixed time grid with a fixed time resolution. So instead, for event-based training, you typically like EventProp or FastND from Gölz et al. You basically just rely on the spike recordings. And since the number of required voltage samples is typically determined by the membrane time constant, and the number of observed spikes in spiking neural networks is typically much lower than that, the spike or event-based learning in general is considered more information efficient. So we have, to show this, we have implemented EventProp on our BrainScales 2 system and verified it against surrogate gradient-based models as well as an analytical event-based implementation from Gölz et al. And for a network with 120 hidden neurons, we observed, you measured 2,280 membrane samples, where we measured the membrane over 38 microseconds with an average sampling rate of about 500 kilohertz. And each of those samples has 8 bits. And for the EventProp model, we observed 146 spike events, where each spike event has 24 bits, like 8-bit for the label and 16 bits for the timestamp. And this resulted in an overall information gain of about 1 order of magnitude, while also maintaining the classification accuracy compared to surrogate gradient-based trained models. Yeah. So this also shows that analog training on analog event-based hardware greatly benefits from data sparse input and output encodings. So instead of having loss functions that rely on membrane potentials, you want to have loss functions that work on spike times directly, for instance. So most gradient-based spiking neural network optimization frameworks that are out there typically represent time as an additional tensor dimension with a fixed time step, as we also do with HX-Torch. And yeah, but typically if you have like event-based neuromorphic hardware, the return data types are typically events, and you want to have event-based optimization software that can work with explicit time data structures that complements basically the returned data type from the hardware, such that all the translation overhead is not necessary anymore. And also working directly on spike or event-based data structures enables high temporal resolution, because having fixed time steps in your data structure typically implicates a loss of information. So we have, for this, we have worked on our Jackson framework, which is our latest high-level optimization framework to optimize models on brain scales. And this enables time-continuous event-stepped rather than time-stepped gradient estimation based on chucks. And this can work directly on this data structures like that have explicit time, which means that you basically optimize on data types which are lists of spike trains, for instance. And while also supporting like the simulated forward pass, we also have means for offloading the forward pass to neuromorphic backends, like for instance the brain scales. And if you're interested, you can check out the NICE conference paper or code on GitHub. So now the QR code is gone again. But so to summarize, having larger scale experiment emulation is important to faithfully represent future scale systems, and for doing so, like larger than substrate network model emulation, we have means for partitioning the network in high-level software, and to run those models on the current single-chip brain scale system. And yeah, we also push towards event-based methods for software for which promises to speed up and scale up training on larger networks. And yeah, so the next step for us is to scale up to larger data sets and networks, and also investigate algorithms for handling large data sets as well as models, which typically require certain methods that need to be investigated, like having normalization techniques or ensure that your model evolves like in dynamic ranges that are feasible on hardware. So with that, thank you very much. I'm happy to take your questions.
Thank you, Elias. Are there any questions for Elias here? I see there's one question.
Yeah, hi, I'm Sebastian from Forschungszentrum Jülich. So my question would be, how much of your approach can you translate to fully digital systems? Because essentially, if I understand correctly, the communication of spikes, both on-chip and off-chip, is digital spikes in your system. So is there anything that is specific to analog hardware, or can we directly translate this event prop also to digital hardware?
Well, to which part you're referring to?
Especially the event prop algorithm for learning.
Yeah, for sure. I mean, it can be just implemented on digital devices as well. I'm not sure it has been done yet, but of course you just need a device that basically simulates your neuron dynamics, and then, yeah, I'm not completely sure what your question is here.
I mean, is there anything specific about this algorithm where the analog part benefits from?
So first of all, you need much less data, which to be transferred. Then you can optimize your model on hardware just based on the spike observations, and which basically allows you to not. Yeah, I'm sorry, I don't get the question completely. But
we can also discuss later.
Yeah, for sure. Yeah.
Thank you. I can see there's another question.
Yeah, one short question, actually, Henk Corporaal from Eindhoven University. If I understood correctly, you can learn both with the inference engine, the real inference engine in the loop, or not. So you have also a model of the machine. I was wondering, did you see big differences between the two types of training?
So you mean between
training with the real machine, analog machine, in the inference phase, versus apparently, I guess, a model of it?
Like just having a simulated forward pass instead?
Yeah.
Sure, there are differences. I mean, it depends on your data set and your task, but typically you can get very close to your simulated performance, so to speak. Yeah, for instance, for the Euroset dataset, as you've seen, we had like a 9% hardware penalty, comparing simulated inference accuracy versus the emulated accuracy on hardware. But for instance, we also have seen results for yin yang, for instance, where the hardware penalty is typically very low. Yeah.
Okay, thanks.
Thank you. Thanks, Elias.